talking about, spectral triples in a metric approximation sense, more specifically ones defined on fractal curves. Oh no, why did it do that? Okay, so really in terms of my work, there's two main motivations. One of them is finite approximation of fractals. And so why would you develop a theory of finite approximation of fractals? And that's because there are lots of natural phenomena that mathematicians would call fractal. As you can see, fractured or rough from some of these examples in the pictures. And the problem being that a purely theoretical fractal, it's an infinite object. So any occurrence of fractal structure nature is by necessity going to be finite. And well, we have many important physical processes that are described by differential equations, but the problem being that, their solutions are usually formulated in terms of operators on smooth manifolds. So if we could extend, come up with a framework that includes manifolds so that we can extend these methods to fractal spaces, that would also help us better understand how fractal structures arise and evolve in nature. So to metrically approximate differential structures on fractals, we use tools from non-commutative geometry. And well, why is that appropriate? Well, first of all, essentially non-commutative geometry, it studies the geometry of a space by analyzing the algebra of functions on a space. And so even though fractals don't admit smooth paths, they do admit continuous functions. So from the perspective of non-commutative geometry, fractals and manifolds are on the same footing. So what are we have two main tools from non-commutative geometry. And the first is spectral triples. And that's because they could be viewed as a generalization of differential structure. And the second is the Gromov-Hausdorff propinquity. And that's because it can be viewed as an extension of Hausdorff distance to function spaces. So from non-commutative geometry, we have our generalization of differential structure. We have our metric. So what about our fractals, our fractal curves, and our framework for approximating them? So here's our motivating example, the Sierpinski gasket. And the reason being because this is a fractal that satisfies a lot of non-equivalent definitions of fractality. So in the fractal geometry community, there are many non-equivalent definitions, and there's a lot of different phenomena that everybody agrees should be called a fractal, but they might not satisfy all of these definitions. And since the Sierpinski gasket satisfies a few of them, then that's a good test case. So for instance, you can see that it exhibits self-similarity, and later today we'll see something that isn't perfectly self-similar. And of course, fractals are not going to be perfectly self-similar in nature. So this definitely has self-similarity. It also has fractional Hausdorff dimension. So that's another feature that actually, so some things like the Cantor-Lebesgue, the graph of the Cantor-Lebesgue function is agreed to be a fractal, but it doesn't have fractional Hausdorff dimension. Same thing with like certain paths of particles in space. They might have also an integer dimension, even though we agree from the super complicated aspect of them that they're fractal. But most importantly for our purposes, this is a fractal that could be written as the unique fixed point of an iterated function system for the Hausdorff distance. So for an iterated function system, basically what you need is a complete metric space and a set of contraction mappings. And so here is the particular one that gives us the Sierpinski gasket. And of course, our complete metric space is R2. So here this is the definition of fractality that's most relevant for our work since we have a complete metric. So here is our framework for approximating fractal curves like the Sierpinski gasket. So a piecewise C1 fractal curve, it's a compact length space. So what that means is that the distance between any 2 points in the space is realized by the length of a path in the space. And so it's a compact length space that satisfies the following 2 properties. So first of all, the space can be written as the closure of a countable set of parametrized curves. And furthermore, this set can be ordered by decreasing length. And the role of this second axiom is that it tells you that the endpoints of the set of parametrized curves in the first axiom, that they're dense in the space. But most importantly, it gives you a handle on the geodesics in the space via the set of curves in the first axiom. So as you can see, many fractals that can be constructed via an iterated function system, they satisfy all these axioms. And this framework, though, is broader because we don't encode some particular set of contraction mappings. And so therefore, it allows for descriptions of more complicated examples of fractality. So the class of piecewise C1 fractal curves, it includes the Sierpinski gasket, but also includes this, which is the harmonic gasket. And that's another important example of fractals in the theory of analysis on fractals. And first of all, so we could see that one difference is that this is self-affine rather than self-similar. So also here for the harmonic gasket, any 2 points can be connected by a C1 path. And that's obviously not the case here in the Sierpinski gasket. It might be a piecewise C1 path, but it's not going to be a C1 path like in the harmonic gasket. And then lastly, the reason this is also important is because it's the fractal on which there exists the most developed version of Riemannian geometry. So for this particular fractal, there are formulas for energy and for geodesic distance, and they involve measurable analogs of Riemannian metric, Riemannian gradient, and Riemannian volume. So it's one in which this sort of, goal has been accomplished for this particular fractal. Okay, so to give an idea of the subject of analysis on fractals, I'm going to give an overview of the theory of harmonic functions on the Sierpinski gasket. So harmonic functions on the Sierpinski gasket, they're used in the construction of the harmonic gasket fractal, which we saw in the previous slide as I discussed some ways in which they fundamentally differ. So remember that in the classical case, harmonic functions on the Sierpinski gasket, they're energy minimizers for certain boundary values. And here, so these vertices of that initial, of a sort of unit equilateral triangle, those are usually viewed as the boundary values, the boundary points for the Sierpinski gasket. And using the contraction mappings from the iterated function system construction of the Sierpinski gasket, any vertex can be written as the image of one of these 3 points under some sort of n-fold composition of these contraction mappings. So that's what this sort of vector encodes. And so the set of vertices obtained in this way, which is what's signified by V star, those happen to be dense in the Sierpinski gasket. So if we have, and furthermore, okay, so before I go on, another thing about the Sierpinski gasket is that it could be written as the closure of an increasing union of a certain sequence of finite graphs. So the energy on each nth level approximation is defined on the vertices in that graph that are each connected by an edge. So, so an extension of a function defined on the nth level graph approximation to one on the n+1th graph level approximation that minimizes the energy, that's called the harmonic extension. of that function to the next level. So then a function is called harmonic if given its values up here at the boundary, it happens to minimize the energy for each additional level. So a real valued harmonic function on the boundary of the Sierpinski gasket, it can be uniquely always, so it turns out this extension, so if we define it on those 3 boundary point values, then the extension to the entire gasket, the harmonic one, it's always unique. And so due to Kagami, then there's also Laplace, so this is where, for interest of us, because we're interested in operators on manifolds. So in this particular setting, we have a Laplacian type condition. So that is, if we take the renormalized energy and a probability measure on the Sierpinski gasket and define the Laplacian operator in this way, then the harmonic functions, they happen to coincide with those that vanish under this Laplacian. So in that sense, this is a very well-developed example of a differential operator on a fractal that, suitably generalizes Q properties from the Riemannian manifold setting. So how does one construct the harmonic gasket? So first you start with the 3 Dirac delta functions for each of the boundary points of the Sierpinski gasket. And remember that anything defined on the boundary has a unique extension to the entire fractal. So you take those unique harmonic extensions. And using those 3 harmonic functions, you define this following homeomorphism on the Sierpinski gasket. And so one way to get the harmonic gasket is as the image of the Sierpinski gasket under this homeomorphism. You could also, via this, construct some contractive affine maps and then take it as the unique fixed point of that iterated function system. And so the theory of harmonic functions, though, on the Sierpinski gasket, it relies on this particular sequence of finite graphs. And many fractal curves, they can be approximated by simpler structures like finite graphs. And of course, the Sierpinski gasket is one example. And our goal was to identify conditions under which differential structures defined on fractals can also be realized as a metric limit of differential structures defined on their approximating finite graphs. So with the Sierpinski gasket as our motivating example, we were able to extract what properties we would need, what properties would need to be exhibited by such a sequence of approximating spaces. And what we wanted was so that our spectral triples on these approximating spaces, they would converge under the spectral propinquity metric to the spectral triple defined on the entire fractal. So we also wanted so that our arguments could be applied to any piecewise C1 fractal curve, not just the motivating examples, and also to any piecewise C1 fractal curve for which you could determine some sequence of approximating spaces. And so we identified that those approximating spaces had to have the properties that I'm going to talk about on the next slide. So these properties are codified in this definition. So this is a definition of an approximation sequence for a piecewise C1 fractal curve compatible with a given parametrization. So given a piecewise C1 fractal curve, we have by definition from that first axiom, we have a decomposition of it into a countable set of parametrized curves. And also remember that it can be ordered by decreasing arc length. So what that means is that then we have an enumeration of these parametrized curves. And so we can write an increasing function that tells us up to which parametrized curve to take our union over to define each approximating space. And we define the vertices to be the endpoints of these parametrized curves. And so dn then signifies the restriction of the geodesic distance to each of these approximating spaces. And Furthermore, we added some other properties. And so that includes that such a function defines so that the sequence of subsets of the piecewise C1 fractal curve. So what we needed was we needed it to be kind of dense or distributed throughout the larger limiting space in a particular way. And we also wanted the geodesic distance between vertices in each approximating space to, we wanted those to be geodesics also when embedded in the larger space. So having these two properties, that allows us to get enough of a handle on the function spaces so that we can apply our tools from non-commutative geometry. So here is a set of parametrized curves, and they're ordered by decreasing arc length, and the closure of their union is a Sierpinski gasket. Each finite graph in our approximation sequence for the Sierpinski gasket compatible with this parameterization, it's a union of equilateral triangles of decreasing diameter, and you can see that in this formula. So again, what this is encoding is that we have this ordering by decreasing arc length, so up to which of these parameterized curves do we take the union over to define each approximating space. So you can also see that, so let's look at the next slide. So again, you could have a different parameterization. So you do for the harmonic gasket, but they can have the same approximation sequence. Okay, so remember our generalized differential structures on our class of fractal curves, those are given by spectral triples, and spectral triples are due to Kahn. And so our spectral triples, so we have a C-star algebra, we have a unital C-star algebra, we have a Hilbert space, and we have a distinguished operator on that Hilbert space, and we also have unital representation as bounded operators for the C-star algebra on the Hilbert space. And so with respect to that distinguished operator on the Hilbert space, it has the property that the set of elements in the C-star algebra with which its commutator is densely defined and extends to a bounded operator on the Hilbert space, that's dense. So based on considerations from quantum mechanics, the differential of an element in the C-star algebra is given by its commutator with this operator. And so therefore, you can view this denseness condition as analogous to the denseness of C1 functions in C of X. So we also have a compact resolving condition. And what this does is ensures that the eigenvalues of this operator, that they exhibit properties that are suitable for extraction of geometric information, like measure and dimension from spectral data. So if all of these ingredients are in place and our representation for the C-star algebra is faithful, then our triple qualifies as a spectral triple, and that distinguished operator, then it's called a Dirac operator. So the spectral triples in our work, those are due to Lapidus and Sarhad, and their construction gives us a spectral triple for any piecewise C1 fractal curve. So again, remember that for a piecewise C1 fractal curve, we have a decomposition of the fractal curve into parametrized curves. So what this spectral triple is, part of the construction, is that it is a direct sum of spectral triples of the following form. So we have a spectral triple for each parametrized curve, and it's composed in the following way. So we have, for our Hilbert space, we have the L2 functions with respect to normalized Lebesgue measure. For our C-star algebra, we have C of X, with the representation being by left multiplication, with the composition of this function with this version of the parametrized curve. We also have our Dirac operator is defined like this with respect to this canonical orthonormal basis. And what Lapidus and Starrett showed was that the direct sum, this countable direct sum of all these spectral triples is also a spectral triple, because you're not guaranteed that that's going to be the case for the countable direct sum of spectral triples. So they showed, based on the geometric properties encoded in that first part of the definition of piecewise C1 fractal curve, that was enough to guarantee that such a construction is a spectral triple. So, but more importantly for our purposes, they also showed, using the properties of such fractal curves, that the geodesic distance down here, which we'll see again on the next slide, that it can be recovered for this from the spectral triple. And so in the larger scheme, as I stated earlier, remember that a motivating example or a motivating question is, how can Riemannian geometry be extended to include fractals? And in Riemannian geometry, the geodesic distance encodes the geometry of the manifold. So as you can see, the classical definition over here, it's formulated using paths in the space. Again, not good for a fractal. And well, this is dual to the non-commutative geometry formulation. And where we have operator theoretic data. Okay, people can see that. And so here we have operator theoretic data, and we have the C-star algebra, C of x. We have the Dirac operator, and we also have the representation. And in the prototypical case of a compact spin Riemannian manifold, these two distances here, they coincide. But this is not true in the general case. So part of the art in developing spectral triples beyond this originating prototypical setting is to identify spectral triples that recover important aspects of the geometry. So some spectral triples might also recover the Hausdorff dimension, some the Hausdorff measure, some all of them, or 2 out of 3 of them, or other sorts of important geometric quantities. So for our purposes, since the Lapidus-Sarhat spectral triple gives us, we can recover the geodesic distance from it. That makes it useful for this greater scheme of analysis on fractals. So then the question becomes, how do we build up the function spaces on our piecewise C1 fractal curve so that we can get up to the level of putting a metric on our spectral triples for the fractal and our spectral triples for the finite graphs in an approximating sequence for the fractals? So our approximation sequence for the Sierpinski gasket, so this traditional view of it as is this particular increasing sequence of finite graphs, well, it converges with respect to the Hausdorff distance for increasing n to the Sierpinski gasket. So remember our non-commutative metric, it's an extension of this distance to function spaces on the fractal and on our approximating sequence. So if each of these, if each finite graph in this sequence is equipped with their respective geodesic distances, then the corresponding compact metric spaces, they converge with respect to the Gromov-Hausdorff propinquity metric to the compact metric space for the fractal with respect to geodesic distance. So what's a natural way to associate a function space if we have, so what's a natural function space to consider if you have a compact metric space? Well, that is the algebras of Lipschitz functions. So what is that? So if you take C of x, you equip it with the Lipschitz semi-norm associated to that metric. And well, what metric can be applied in this setting? Well, we can apply the Gromov-Hausdorff propinquity metric because these Lipschitz algebras are prototypical examples of quantum compact metric spaces. So what is a quantum compact metric space? And let me also, before I go on, specify that this generalization is due to Riefel. So quantum compact metric spaces, these are non-commutative generalizations of algebras of Lipschitz functions. And the Gromov-Hausdorff propinquity is a complete metric on these structures. And remember again, so that's why iterated function systems, those are the appropriate lens to view our prototypical examples. So one of the key components was a complete metric, so that the Gromov-Hausdorff propinquity, that we have, that it's equivalent to a complete metric, then this is the appropriate tool for non-commutative geometry. So the sort of two key components is we have a unital C-star algebra, and we have a semi-norm that exhibits the following properties. So here's where you can see the analogy with the Lipschitz functions. So the semi-norms defined on a dense subspace of the self-adjoint elements of the C-star algebra. It satisfies some kind of Leibniz inequality, and it vanishes on the scalar multiples of the identity. And so you can see here where, because it's no longer the Lipschitz semi-norm coming from the metric, but we still keep that property in the non-commutative case. And so the second key property is that the Monge-Konorovich distance on the state space, defined in this way from the semi-norm, it turns out that that metrizes the weak star topology of the state space. And just to remind you that the state space, that's the set of positive linear functionals of norm 1. So we have so that we have a metric from that semi-norm that metrizes, a pretty fundamental topology to put on linear functionals. So when our semi-norm possesses all these properties in relation to our C-star algebra, then our pairing is a quantum compact metric space. And also this turns out that this semi-norm is also called a lip norm. So how does non-commutative geometry move beyond the classical setting? Well, we allow for us to consider C-star algebras beyond C of X, and we also consider semi-norms beyond the Lipschitz semi-norm, so long as we have all these conditions present. Okay, so the spectral propinquity metric, that's actually an extension of this complete metric on the space of quantum compact metric spaces. And it's extended to spectral triples in the following way. It's defined on particular spectral triples. So this is on spectral triples that induce quantum compact metric space structure in a particular and very natural way. So we have the spectral triple, we have the C-star algebra, we have the Hilbert space, and we have the Dirac operator. This is the canonical way to construct a semi-norm from the Dirac operator. So the norm of the commutators with that Dirac operator. And so if you take that particular canonical semi-norm, and if the C-star algebra equipped with it gives you quantum compact metric space structure, then that spectral triple is called a metric spectral triple. So the spectral propinquity, it's a metric on the class of metric spectral triples. And most importantly, before I go on, let me just also say, what are some additional things that you also get for this? Well, like as in why extend it to this space? Well, you get some extra information about, there's an additional module structure of the Hilbert space over the C-star algebra, and it also takes into account the action of the Dirac operators on the Hilbert space. So it is an extension in the sense that we also consider different aspects of the Hilbert space and the Dirac operator. happen to be encoded in this metric. So, so then what do we get if we have distance 0 for two metric spectral triples with respect to the spectral propinquity metric? So, why define this? So, because then you get unitary equivalence of the Dirac operators. So that's the payoff. And well, why is that important? It's because, a lot of really, in terms of the geometry, and usually you might define things in terms of the spectrum. So getting unitary equivalence of the Dirac operators means that you also get, super strong equivalence with the spectrum. And also, of course, because this is an extension of the propinquity metric, then we also get a sort of strong form of equivalence between the underlying quantum compact metric space structures. So in terms of basically the semi-norms play with each other in this particular way. So going back to our setting of the Lapidus-Sarhad spectral triple on a piecewise C1 fractal curve, let's first consider the example of the Sierpinski gasket, for which we have an approximation sequence compatible with the parametrization. So we have a spectral triple that is a countable direct sum of spectral triples. We want to compare this spectral triple with a spectral triple that is a direct sum of a finite subset of spectral triples, each determined by our approximation sequence. So again, from this approximation sequence being, it tells us up to which particular parametrized curve to take our union to define an approximation space. And so while both spectral triples can be shown to be metric spectral triples, so it's appropriately in our space. And the main result is that for increasing n, the Lapidus-Sarhad spectral triples on the nth level approximation of the Sierpinski gasket converge to that on the entire gasket with respect to the spectral propinquity. So in other words, for increasing n, the Dirac operators in our spectral triples get closer and closer to being unitarily equivalent. And again, that means that the geometric information that we can extract from the spectral triple, which relies on the spectra of the Dirac operators, then that information is pretty much, it's getting closer and closer to being the same. So and here's where I've highlighted. So again, the arguments are such that they work beyond the Sierpinski gasket for any piecewise C1 fractal curve. So what this means is, because our arguments apply to any piecewise C1 fractal curve for which we can define an approximation sequence with all the things in our definition, then we can consider more complicated fractals in the Sierpinski gasket or the harmonic gasket. And we can define spectral triples on them by first constructing spectral triples on simpler approximating spaces. So, and so here's where you can see all I have to do is because of the nature of these arguments, it still applies to, I replace Sierpinski gasket with any piecewise C1 fractal curve. So in my current work, which I'll start presenting on the beginning of next year, so I'm working on the following generalization, hence expansion of the class of fractal curves for which our techniques could be applied. And it's a generalization because this is not a piecewise C1 fractal curve. And so this is another fractal. This is the stretched Sierpinski gasket. You can see that it's not self-similar, right? Because these these intervals make them not self-similar. It does have a fractional Hausdorff dimension that depends on this alpha parameter. This alpha parameter, you can, there's a formula for what then the corresponding Hausdorff dimension will be. There's also an iterated function system. It's more complicated than the one for the Sierpinski gasket. There we had 3 contraction mappings. Here there are 6. And the first, and some of them, well, 3 of them will give you these spaces. The other 3 will take the images and map it to intervals. So it is a more complicated one, but still satisfies all the different requirements of an iterative function system. And so it has been shown, so that's in the literature, that for the Hausdorff distance, the stretch gasket converges to the Sierpinski gasket. So, so we have this more complicated example that for the Hausdorff distance can be shown to be a sort of relaxation, right, of the Sierpinski gasket. And so remember that the spectral triples for Lapidus and Sarhad, that those are, when you define on each of the pieces, each of the parametrized curves, you define that particular spectral triple. The countable direct sum is a spectral triple. Well, so you can't say that here because it's not a piecewise C1 fractal curve, but Andrea Rauser-Rivera went and worked out that that same construction for this particular case gives you a spectral triple. So that's part of working in this setting. Then I'm using that also as like a sort of prototypical case for what is a more general class of fractals, for which this is the motivating example, which I'm going to call them almost piecewise C1 fractal curves. And so I'm working on showing that the spectral triple on this fractal, that it converges to this, as this alpha parameter goes down to 0, which again encodes these lengths of these intervals, that it converges to the spectral triple on the Sierpinski gasket. So of course, again, this is going to be a motivation for a prototypical case of my more general class of fractal curves. And again, in terms of expanding the class of fractal curves for which we can metrically approximate important kinds of spectral triples. And again, the spectral triple is important because of us being able to recover the geodesic distance on the space from the spectral triple. Okay, so here is another example of a well-known fractal. So this is the Sierpinski tetrahedron. And the point being is that, well, it is not a fractal. Well, it doesn't live in just 2 dimensions, right? It's in higher dimensions. And so not only would we want to consider, the next dimension up, but, what is an appropriate generalization of piecewise C1 fractal curves to higher dimensions? Because we want to be able to approximate higher dimensional fractals and understand them. So what are kind of the essential properties that we need to take with us into higher dimensions? What sort of things do we need to add so that we can still have approximation properties and define spectral triples that, are important in terms of giving us geometric quantities that we want? And so before we can, and we also want it to, have properties so that we need to identify what the simpler approximating spaces, what properties those would need to have, so that we could define spectral triples on them, and spectral triples that are metric spectral triples too. So here's another. This is another fundamentally different fractal. So instead of going up to higher dimensions, this is like topologically just inherently different. So this is the Sierpinski carpet. And this is definitely not a piecewise C1 fractal curve. In general, how does it differ from the Sierpinski gasket? Well, Sierpinski gasket is sort of one of the, and also the harmonic gasket and the stretch gasket. These are what are called finitely ramified. It means that you could remove a finite number of points and entirely disconnect the fractal from pieces of the fractal from the rest of the fractal. And there's much more developed tools for analysis on such fractals. So what makes the Sierpinski carpet so much more difficult is that you can't do that. You can't just remove a finite number of pieces and disconnect the whole thing. And so this is, like those kinds of fractals are called infinitely ramified. And so they're an entirely different class of fractals, and one that isn't so well understood in the literature of analysis on fractals. So I'm learning random conformal geometry. I've been studying that I started studying that this summer. And to what end? Well, to define a spectral triple on the Sierpinski carpet. So there's some techniques there that make it appropriate for this task, and we'll see how that goes next year. Okay, so what is some future work? So first of all, definition and study of a fractal manifold. So the aim being to continue developing tools from non-commutative geometry to describe and understand a notion of generalized manifolds that include fractals. Next one is classification of C-star algebras on fractals. So, there's a lot of reasons for this. So in a more technical sense, the C-star algebras are key components of the spectral triples and the quantum compact metric spaces. But also in terms of even Gelfand duality, there isn't much out there at all on a classification of C-star algebras on fractals. So really the one really known thing is that, so if you have a unital approximately finite dimensional C-star algebra, then for the Gelfand duality, that corresponds to C of X, for X being a totally disconnected compact metric space. But beyond that, so therefore for a Cantor set. But beyond that, there is no classification of C-star algebras on other fractals. So of course, the first natural one that I've been looking at is the Sierpinski gasket. So that is not even known at all. Like if X is a Sierpinski gasket, then what is C of X? So it's definitely not an AF algebra, because one of the things about the Cantor set is that it's totally disconnected. And all the fractals I've talked about here, because they've got their length spaces, they're all connected. So it just can't be an AF algebra. So the point being, what kind of C-star algebra is it at all? So even for the unital commutative case, what kinds of C-star algebras are they? And so that's a natural thing to kind of get in order before you kind of start to look at what are some non-commutative C-star algebras associated to some fractals. And also because we have this, complete metric on structures associated to C-star algebras, well, then of course, then we could compare, commutative ones with non-commutative ones. Okay, so another important avenue for future work is approximation of Laplacians on fractals. And again, for going back to this theme of how do we generalize the manifold setting being important because we have solutions of differential equations using particular operators like the Laplacian defined in a manifold setting. Well, a spectral triple, you can use it to define a measure, right? So to define a Laplacian, you need a measure. If you use a sort of tool called a Dixmuir trace, then you could use that to determine a measure from the spectral triple. And then, the hope would be, do you get like a Laplacian from a certain spectral triple? It's not only that, do you get Laplacians that have been studied before you even start to consider, oh, here's a better Laplacian. And maybe even hopefully you would kind of maybe discover something important about Laplacians that kind of were hidden in the classical case or the known case or in the non-commutative case. So also understanding things about structures of Laplacians, but coming from the direction of the spectral triple. And then finally, well, I am a non-commutative fractal geometer. I don't really know too many others. Then the other big one would be non-commutative fractality. So this is kind of so what would a non-commutative fractal be? I mean, first of all, there are all these definitions of fractality out there. So, what is a non-commutative fractal is just kind of a fun thing to think about. But also, I mean, of course, there are all sorts of rough structures that happen in, like, say, physics or quantum information settings. So you need to kind of have some of the theory developed to be able to kind of describe some of this stuff. So since we're working with complete metrics, then, a sort of natural thing would be, what's an appropriate set, we have a complete metric, what's an appropriate set of contraction mappings that happen to be maybe, in a sort of non-commutative setting. And so, what's the right IFS in a non-commutative setting with our complete quantum metric? And also like one that gives something, that people study. Like, so from all the different things people study, could we, get it back with this IFS? I guess I've also thought maybe too with C-star dynamical systems and maybe with the symbolic dynamics too. So bigger question, what is a non-commutative fractal, or what would it look like, or what could it be? And hence my motivation for learning more about the greater wide world of operator algebras and operator theory so that I could have better, tools and perspectives in that sort of big question. Thank you.